Hello everyone. I am audible. The content are visible or not? So yesterday, okay, all is well. I think some light issue. So so tomorrow I will discuss from last day. Yesterday I am discuss about some identity matrix or unit matrix. So in last class we study about some identity matrix. Okay, and light is clearly visible. Everything is fine or not? From last day. Please clear me. Yesterday I am discuss about some identity. Okay. So according to my thumbnail, you see today class is related to idempotent matrix, involuntary matrix, or identity matrix, or anything. Okay. So today class we study about some identity matrix or unit matrix. So student, what it means? Which type of identity matrix or unit matrix deals about the discussion about for identity matrix or unit matrix. So today the scalar matrix A whose diagonal element R1, it means unity, is called identity matrix. And some example related to identity matrix are like this. These are diagonal type 3 cross order 3 type matrix, and here is the some identity matrix. So identity matrix which have diagonal element R1 or unity. So we can say that it is the which type of matrix? Identity matrix or unit matrix. Okay. Come to the next point. Here we discussed in earlier and in yesterday last day we discussed about idempotent matrix also, and what it means. Idempotent matrix, it means a square matrix which is called idempotent matrix if its square is identically equal to itself. What it means? It means its square is identically equal to itself, so we says that it is the idempotent matrix. So let's some example about idempotent matrix are. So we take some order n cross n and comma in and equal to a, which is some entries like I 00 triple zero and something entries like this. Okay, so clearly a point I will talk about the idempotent matrix is like you have some square matrix and it keeps identically equal to itself, so he says that it is the idempotent matrix, and these examples are related to idempotent matrix. So these are the I think you should must be, I think all is clearly visible because here is some light issue and also my face clearly. So example 0 point when we take zero matrix. So here is some A, B, C, D type matrix. So you see here some element are a unity. Here is the element are unity, and this is also unity, and this is also unity. So it shows the square matrix and idempotent matrix which have identically equal to itself, which is known as square idempotent matrix. So now come to the next point, which is some related problem to about this idempotent matrix. So we discuss about some problem like this. So what the problem tells? The problem tells that find the number of diagonal matrices of order n which are idempotent. So how to solve this problem? Take question. Take some diagonal matrix which have entries like t1, d2, tn, and when a square it, then it comes d. So itself it comes, so it shows that idempotent matrix. When we square a diagonal matrix, it comes by itself. Then we say that this matrix is idempotent matrix, and their entries like this: one less or equal to iota and less equal to n. So we say that it is the idempotent matrix, and d equal to 0 or 1 or iota. The next point is that therefore number of diagonal matrices of order n which are idempotent. What it means? It means if A is idempotent matrix, then iota minus A is also a idempotent matrix. So when a matrix order n, then it comes their idempotent matrix is 2 to the power n. If A is an idempotent matrix, then iota minus A is also idempotent matrix. So given a data A is idempotent matrix, that is A square is equal to A. When we square two idempotent matrices, it comes. When we square some two unity matrices, it comes also unity. Now I minus a square, which is equal to some a minus b type formula we use here: a square minus 2ab plus b square. So when we square a square square, it comes a, and these are also comes I minus a type, because when we uh, idempotent a is given idempotent data, so yes, a square is equal to a, so it comes only a here. When we put a here, when I minus 2a plus a, it's also come the I minus a, because here we subtract this data and it comes I minus a. So we say that here we see that I minus a square is equal to I minus a. So these are the necessary outcomes for this idempotent matrix. Now come to the next point. Here there are some example related to this. Take a matrix A which is equal to their entries 1 by 3, 1 by 3, 1 by 3, 1 by 3, like this, and is idempotent and order 3 cross T type matrices. So then I minus A is equal to, when we subtract I minus A, something identity matrix subtract from this matrix, so it comes this type of matrix. It is also idempotent matrix. So necessary things is that when we use I minus A in whole square which is equal to I minus A, so it gives you some data like this. So some note point are there. Okay. Let me check on YouTube. Everything is fine or not. That is which is equal to I minus. Okay. The here is the proof here, because in my videos I am not clearly visible the proof portion in this. So first of all, then in idempotent matrix we multiply, post multiply, then it comes a square type matrices. Okay, and go to the next slide. This also gives you some idempotent matrix. So the outcomes for related for these, which is a square is equal to a and b square is equal to b. When we multiply, post multiply to each other from equation, in equation first and in equation two we use a post multiply type process. So it gives you a square is equal to a and b square is equal to b. So these are the solution for this. On come to the next slide. Here is some idempotent matrix. Take two idempotent matrix, which is A and B are two idempotent matrices. Then their addition is binary addition is also idempotent matrix. And when we apply this condition, which is equal to AB equal to B equal to 0. So how it proves the problem? So now come to the solution behind this. So point number three. So point number three is basically tell about take some two idempotent matrix and their entries are a square which is equal to a. It's also the example of idempotent matrix and it is clear. So by definition, a square is equal to a, b square is equal to b. Now add their binary addition idempotent if and only if a plus b whole square is equal to a plus b. So now to derive this formula like this, which is a plus b whole square. So a square plus b square plus 2 plus ba, because here is the no any process of 2ab or like this. You know, you may be not write like this. So it comes only this type of matrices. So you write like this ab plus ba. Okay, so it comes like this. So A plus B both imply A plus B, AB, AB, BA. It comes A plus B. So you see here it is a which type of character shows that it shows that you have idempotent matrix when you take two idempotent matrix and one add and it gives you idempotent matrix. So these are the basic solution for this problem. Now come to the next problem, which is also related to this. So now come to the yes, come to one more solution related to this problem. I have problem for yes, it is very important problem for you. Okay, so these type of question always ask in CSIR NET problem, and problem is problem is like this. Take if a equal to 5 triple 1 1 5 double 1 1 1 5 1 and lastly 1 1 1 5. This is matrix. Then find a to the power 50. Okay, a to the power 50 matrix like this. So solution for this problem. Okay, now when you have a matrix A which have entries like 5 1 1 1 5 1 1 and lastly 1 1 1 and last triple 1 5. These are the entry for this matrix. So find for a to the power 50. So how could you find this problem? Okay, so first of all you factorize or you divide like this something. Take some trick about for this. Now here put 4 out. Okay, and take a identity matrix 1 and all entries are 0 from R1, and in R2 only which will make a all diagonal matrix. So here the entries are 0 0 0 0. Okay, when we take like this matrix like this 4 iota plus 4b. Okay, why we take this matrix for this problem? We take a matrix for this problem because B is our what type of matrix? Idempotent matrix. So we take B here, and when we apply concept behind this, take a to the power 50. It comes. It gives you which type of matrices like this. Take some 4 iota plus 4 beta type element idempotent matrix. So these are the element for this. and take another matrix which have entry 1 by 4, 1 by 4, 1 by 4, and 1 by 4, like this entries. All entries are 1 by 4, 1 by 4, 1 by 4. Okay. Wait a minute. Why am take here some points like this? So wait for a minute. Let me check this. Okay, student, any problem? Okay, wait for minute also because I am confused for this problem. Okay, if A have entries, then find A to the power 50. How you find for this problem? Okay. Do you have any doubt or any comment? Tell me. Type ND for no doubt and type D for doubt. Okay. And all entries are same for 1 by 4, 1 by 4, where B is our idempotent matrix. Okay. Now come to the next point. So therefore, some result. So therefore, a to the power 50, which is equal to 4 to the power 50 iota plus 8 to the power 50 minus 4 to the power 50 and also multiply b. So these are the solution for related problem. Okay, take a 4 cross 4 matrix on with a 5 on the diagonal of 1 everywhere else. So these are the solution. How could you check inverse of A? There are very lengthy solution for this given by AI. Okay, so now come to the nilpotent matrix, which is very interesting topic for you. Okay, so come to our next topic, which is our nilpotent matrix. What do you understand by nilpotent matrix? So, if you have any square matrix, okay, which type of matrix? A square matrix, and there exists a positive integer m such that a to the power m equal to 0. So, for any positive integer of k such that a to the power k equal to 0. So these are known as the index of nilpotent matrix and also which is called as nilpotent matrices. So what the definition of nilpotent matrix? So nilpotent matrix is nothing but a square matrix. A square matrix A is said to be nilpotent matrix if there exists a positive integer, there exists a positive integer m such that equal to 0. This is our nilpotent matrix. The smallest positive integer. That's the smallest positive integer key such that a to the power k equal to 0 is known as known as index of nilpotent matrix. So nilpotent matrix is what a matrix, a square matrix A, which is said to be nilpotent matrix if there exists a positive integer m such that a to the power m equal to 0. It is the smallest positive integer case such that a to the power k equal to 0, which is known as an index of nilpotent matrix, which is the smallest positive integer which is u for the e to the power k or something like elementary integer like this. So we can say that it is the nilpotent matrix. So let us see some note for this. So note number first is what? So note to first it says that if zero matrices zero matrices have index nilpotency nilpotency 1, and point number 2 is what? All non-zero nilpotent matrices have nilpotency less or greater or equal to 2. So all non-zero nilpotent matrices have nilpotency greater or equal to 2. So now take some example related to nilpotent matrix. So we take in the second slide for this. Okay. Uh, the two note what it tells. First note says that zero matrices have index or index may be nilpotency 1. So zero matrices have nilpotency 1. So zero matrix like this a to the power 0 which have nilpotency which 1 type. So all non-zero nilpotent matrices have nilpotence which is greater or equal to 2. Okay. So these 2 points keep in your mind. So now come to the next point, which is an example for nilpotence matrix. Take an example for this. So the example is let A equal to the entry is like this: 0 1 0 0. Second row is 0 0 0. Third row is 0 0 1, and last row is 0 0 0 1. This is the example of some matrix, and then find a square which is equal to 0. These are the example for this. When we square the term, it gives you a square, then a square is equal to 0. So therefore a is a nilpotent. Wait a minute. Let I am very tired now because lot of coding I am doing and my eyes pain. So just a sleepy tired. Okay. Therefore, A is a nilpotent. Here is the example for this. So A is a nilpotent matrix. Nilpotent matrix of index which is equal to 2. Okay. And some one more example for this. Take one more example for this. So let B which is equal to their entries is 0 1 0 0 0 1 and last is 0 0 0, and then B square is equal to they have entered like 0 0 1 triple 0 and in last is triple 0. Okay, and BQ is equal to entries like 0 0 0 0 0 0 0 0 0. Okay, so this is the basic example for Nilpotent matrix of index 2. So here is the index is 3. Okay. So now come to the next problem, which is related to triangular matrix or something non-trivial matrix like this. So take one more note for this. Okay. So come to the note, and note says that take one note for this. So if A is a nilpotent matrix, A is nilpotent matrix. Okay, note if A is nilpotent matrix of order n, then nilpotency of A which is less or equal to n. So problem here is the problem for this. Consider A which have entries like this 1 0 0 1 1 0 and lastly 1 0 1. These are the entries for a problem, and then find a to the power 1000. Okay, so mainly solution for this problem. So goes to the solution for this. Consider a matrix and then find a to the power 1000. How could you find a to the power 1000? So first of all, take a matrix A and which have entries same like this. So put the entries here 1 double 0 1 1 0 1 0 1. Okay, these are the entries, and a to the power 1000, so it may be changed into some. Take some identity matrix I and some nilpotent matrix B. Okay, so it comes in the form of 100 010 and 001. These are the example of identity matrix, and some other nilpotent matrix. So other nilpotent matrix which is they have entries triple 0 1 double 0 and lastly 1 double 0. So it gives you some I plus B type entries. So where B which is equal to 0 0 0 1 0 0 1 0 0. Okay, and P square must be equal to 0, which is equal to BQ which is equal to also 0. These are the point for this. Okay, so therefore imply take some matrix or rules for this. So take therefore imply e to the power n which equal to iota plus b to the power n, which is same equal to iota plus n c1 b to the power b plus n c2 b square plus which is also dot dot dot, and both equal to iota plus nb. Okay, so therefore we will find a to the power 1000. Okay, which is equal to and their entries 100, 1000, 1110, and lastly 100, and the entries is also here the one. Okay, so these are the basic idea comes from to solve these big type matrices. So when we use some formula for this formula basically you can change some entries like a to the power 1000, or it may be changed into iota plus b to the power 1000. So here what's comes in your mind first of all, you may be change a to the power 1000 like this. It means iota plus b to the power 1000, and it comes iota plus nc1, it means 1000 c1b plus 1000 c2b. Okay, b square, and also it goes to iota plus nb. So these are the basic need for solving, and your must be a take approach for using some iota b type entries and take a power n. Okay, for to solve this type of problem. So come to the point. One last note for this. Then I proceed my lecture and goes and talk about some nilpotent matrix also. So some take some note for this. So a note says that if A is nilpotent matrix, if A is nilpotent matrix of index k, then A which is equal to less or equal to k is equal to 0, that is a to the power k plus r which is equal to 0, and for all r equal to 0, 1, 2, and 3, so on. And a which is less than k which is equal to also 0, so which is not equal to 0. So these are the basic solution for the problem, and one note for related to this problem. And note says that if A is nilpotent matrix of index k type, then a to the power less or equal to k index which is equal to 0, that is a to the power k plus r which is equal to 0. For all r equal to 0, 1, 2, 3 type of element we use for this type of element for r, and a to the power index is less than k which is equal to not equal to 0. So these are the basic note for the problem. And now come to the next point, which is one more note for this. So one two more note for this. So today, now go to the, I think we take some one more problem, and one more problem related to IIT-JAM or like this paper. So one more problem for this. Take one more problem for skew symmetric or symmetric type of problem. Okay, so let a1, a2, which is also goes to an, are skew symmetric matrices, and every pair of matrices anti-commute anti-commute with each other, then a1, a2, dot an is first option is our symmetric, symmetric if n plus 1 by 2 is even. Second option is symmetric if n plus 1 upon 2 is odd. Third option is skew symmetric if n plus 1 by 2 is even. And last option is skew symmetric if n plus 1 upon 2 is odd. So these are MCQ problem. How could you solve this problem? Tell me in the chat box. तो देख लिया जाए भाई यूट्यूब का चैट बॉक्स क्या है. So I am goes to the next point. Okay. Maybe proceed or not. If anyone have doubt, then type doubt. If anyone have no doubt, then type no doubt. Okay. In comment box. Okay. So they have no doubt. So today the problem is something related to JAM or net type problem. So this problem may be asked or not. Okay. So now solve the problem. Now go to the solution for this. So problem is let A1, A2, An are skew symmetric matrices and every pair of matrices anti-commute with each other. Then A1, A2, An is a skew symmetric if n plus 1 upon 2 is even, and B option is symmetric if n plus 1 upon 2 is odd, and third option is skew symmetric if n plus 1 upon 2 is even, and last option is skew symmetric if n plus 1 upon 2 is odd. So come to the solution part of this problem. Okay, so how you solve this problem? So now let us go for solution, and solution part is very interesting for this. So take some element like a1 a2, it goes to an, okay, which is anti-commute with each other, and therefore imply a iota aj, which is equal to minus, because it is skew symmetric now. So entries for transpose is equal to negative part of it. So it may be A transpose which is equal to A minus A for skew symmetric matrix, and A transpose is equal to A for skew for uh, symmetric matrix. Okay. So these are the two basic definition for regarding for this. So the problem is related to skew symmetric. So we take some element for like this. Okay. So this is the anti-commute with each other, and therefore imply a iota aj which is equal to minus aj ai and aj type element for all I which is not equal to j. Okay. So now take a1 a2 basically dot a n minus 1 an transpose, which is equal to an transpose dot an minus 1 transpose and dot a2 transpose, okay, and then a1 transpose, okay. So minus 1 to the power, take some common element for all, take minus 1 to the power n as a common for this sequence. So an minus 1 and dot a2 which is multiple with an. So these are the basic transpose for this. So now take one more step for this. Take minus 1 to the power n and minus 1 to the power n minus 1 and remains element as same as it is, okay. So this comes to the a2, okay. Now it may be minus 1 to the power n and the element is n plus n minus 1 and goes to 2 plus 1, okay. And the remain portion is a1 a2 dot an type, okay. So therefore imply minus 1 to the power n plus 1 upon me 2. So here is a1 a2 and dot an, okay. So these are the basic part for the solution. Now come to the next step for this. So take one more example, one more steps for this. So lastly we see that here minus 1 to the power n plus n minus 1 plus dot plus 2 plus 1 and the element remain as it is. So a1 a2 which is equal to dot an and which is also equal to minus 1 to the power n plus 1 upon me 2. These are the element comes by the further steps, okay. So therefore imply a1 a2 dot an to the power t and it comes a1 a2 a3 and dot an type, okay. If n plus 1 upon 2 is even, okay. And next point is a1 dot a2 dot an if n only if n plus 1 upon me 2 is odd. So these are the two outcomes for our when we use n times of entries for any a to the power n matrix or a to the power n plus 1 matrix. So here we see that therefore a1 a2 dot an is a symmetric if n plus 1 upon by 2 is even and skew symmetric if n plus sorry n plus 1 upon by 2 is odd, okay. So these are two conclusion for this problem. Same for skew symmetric if n plus 1 upon by 2 is even, and next one is symmetric skew symmetric if n plus 1 upon by 2 is odd. So these two point come from the problem. Okay. Now come to the one more problem, which is also related to not important. Okay. So goes to the similar type of matrices. So what we say is that these problem all are related to symmetric matrices and skew symmetric matrices. What the time, dear? So I think it is a 4:47. So now I am close the topic. Okay, we discuss in next class, and in next class we discuss about some Hermitian matrices, which type of matrices we study. In next class we study Hermitian matrices, and next part is skew Hermitian matrices. Skew Hermitian matrices, and further take one more problem for so we see in next class, okay? Because it's the time is I think 4:40. So मिलते हैं next class में. Meet you in next class at same time in same channel. If you are interested to view this topic, so type any comment, good comment in my chat box. Okay. So thanks for watching these videos. So meet you in next class. Okay. We'll meet in next class. So thanks for watching these videos.